Hi folks, welcome back to Physics with Captain Rod. I'm making this video to show how to calculate the velocity and acceleration of a point that's moving on some sort of maybe rigid body. And what we're looking at, we've got this bar here, 0.2 meters long, free to rotate about axis O. At the instant shown, we're going to assume it's rotating clockwise at 2 radian per second and accelerating in a clockwise sense at 2 radian per second squared. This collar, which I labeled C here, is free to move on the bar at the instant shown. It's accelerating down and right at 3 meters per second. And at the instant shown, its velocity vector down and right at 2 meters per second. Now, I've already done a little bit of work on this problem. Let me explain what we're looking at right here. So for starters, I've put a coordinate system in here that I call capital X, capital Y. This coordinate system is going to be fixed in our reference frame and not moving. In addition to that, I put another coordinate system that I call little x, little y, where the little x here is parallel to the bar. And the idea here is this. I'm actually going to work in this green set of coordinates here because a lot of the velocity acceleration vectors we have are going to be in nice directions compared to the green set of coordinates here. All right? So, let's begin. Oh, one more thing. So when we get to the acceleration calculations, it's just kind of a reminder here, there's 3 different types of accelerations that are going to occur in this problem. Okay, and I'd like to kind of review these things. So for starters, we have good old-fashioned centripetal acceleration. Centripetal acceleration, can be calculated by v squared over r, or r times the angular speed squared. Either one, these are equivalent. The direction is always towards the center of curvature. So what I put here is r omega squared. This minus r hat means radially inward. Right? The fact that this thing has an angular acceleration, that's going to give us a tangential acceleration at c. In this picture, that tangential acceleration would be in this direction. Tangential accelerations are equal to r alpha, where alpha is the angular acceleration, or in the language of vectors, it's alpha cross r. Right? Direction is coming from the cross product. And the other type of acceleration we have to deal with is the interaction of this velocity with this angular velocity. So the fact that this bar at the instant shown, or the collar, is moving on the bar with a velocity v, as the bar is rotating, this angular velocity is going to be changing the direction of this blue velocity vector, right? And that gives what's called a Coriolis acceleration. Here's how Coriolis accelerations are calculated. Twice your angular velocity crossed with your velocity vector. So all of these accelerations are kind of relevant here, I believe. I'm going to get rid of this, because we're not going to need that. And let's take a look at what this problem might look like. All right, so we're going to start with the velocity calculation. I'm going to start with this, that the velocity of c is equal to the velocity of O plus the velocity of c with respect to O. Now, and I'm going to rewrite this, velocity O, the velocity of c with respect to O, we got a couple things going on. One, we have the rotational effects. So we can calculate that velocity, or the rotational effect, by the angular velocity of OC crossed with the position vector c with respect to O. Right. In addition to that, however, we have the velocity of c with respect to O in this reference frame. You'll notice that this velocity vector here is the motion of this collar on the bar. That motion is in the plus I direction in our green coordinate system. So I'm going to put plus the velocity of c with respect to O in the x, y, z coordinate system. So I'm going to go ahead and write out what all these terms are equal to. Right? So velocity of O, well, O is fixed in space here. That's not going anywhere. So I'm going to put a big 0 there. All right, so the angular velocity vector cross the position vector. I'm going to go ahead and just do this in a scalar sense. That's going to give us a blue velocity vector in this direction equal to r times the angular velocity. So this is going to be equal to 0.2 meters times the angular velocity of 3 radian per second. And you'll notice this is down and left. And look at our coordinate system here. So this is the plus j direction, so this guy here is going to be in the minus j direction in terms of this green set of coordinates that I've got drawn. All right. Next term, the velocity of c with respect to O in the xyz coordinate system. So you'll notice that this guy right here is moving down and right, magnitude 2 meters per second, and that's in the positive x direction, or what I'm just going to call the I direction here, and we're pretty well done with that. So what we have is that the velocity of c is equal to, we got 6 meters per second in the minus j direction, plus 2 meters per second in the I direction. Almost nothing to this. I'm going to go ahead and write these results up here because we may need some of this later. So velocity of c is equal to, and I'll go ahead and rearrange this. Let's write this 2I minus 6j meter per second. Now, you might be wondering, well, don't we have to move that into this coordinate system? The answer is no. I mean, I've got this velocity vector now. I can put this in terms of any direction I want. I'm just going to call that good. I'm choosing to work in this green set of coordinates here for convenience sake. I'm just going to leave my answer in those green set of convenience, or in that green set for convenience. All right, so now we'll start working on the acceleration vector. I'm going to get rid of this. We're not going to need this anymore. All right, so this one's going to be a little longer, so I'm going to start over on the left here. All right, so the acceleration of c we can write as the acceleration of O plus the acceleration of c with respect to O. Now, the acceleration of O, again, this point is not going anywhere. And what I'm going to do here is I'm going to talk about this. This guy right here, there's three things we have to take into account. And one, there's going to be an acceleration due to the angular acceleration of the bar. Second, there's going to be a centripetal acceleration. You'll notice this velocity vector component here is changing in direction as theta changes. So we're going to have a centripetal that's going to point this way. I'll take that into account here in a minute. And then also this velocity is changing due to this angular velocity. Right? That's going to give us a Coriolis term. And don't forget that c also is accelerating away from O at 3 meters per second. So this is the acceleration of c with respect to O in this set of coordinates. And all four of these effects have to be taken into account. So let's go through them one at a time. I'm going to start with the centripetal term, I guess. All right, so our centripetal term is going to equal r omega squared. That's going to be 0.2, and I'm going to leave out the units. I'll put those last. 0.2 times omega squared. That's going to be this way. Minus r hat is what I put, and what I meant by that is radially inward towards the center of curvature. In terms of my green set of coordinates here, that's the minus I direction. All right, next. Let's talk about the acceleration, or I'm sorry, the tangential acceleration. So the tangential acceleration is going to point this way. Let me go ahead and put that centripetal, or I'm going to call it a normal acceleration that I just calculated. Right? Our tangential is in the direction shown based on the direction of my angular acceleration. It's going to equal r, 0.2 meters, times alpha, the angular acceleration, 2 rad per second. And you'll notice that this is in the same direction as this blue velocity vector, right? So this is the plus j, is kind of up and right, so that's going to be in the minus j direction. Looks like I'm going to need more room. Quite often for these problems to get kind of long here. All right, so I'm going to take this guy. Let's start this way over here, I guess. Hopefully I can get this all in one line. All right, so we got the centripetal term. We got the tangential term due to the angular acceleration of the bar. Next, I'm going to do the Coriolis term. I'm going to write that in vector format for now. So that's going to be twice the angular velocity vector, which is 3 radian per second in the minus k direction. I'm getting that from right-hand rule. Just kind of mentally roll your fingers in the direction of this arrow. Thumb gives you the direction of that angular velocity vector. So twice the angular velocity vector crossed with this velocity vector. That's 2 meters per second. And it is in the I direction. All right, I'm going to go back and make one little change. If I'm going to put the units off in one place, I should do that everywhere. I'm going to get rid of that. What I'll do is I'll put the units at the very end of this thing. All right, so this quantity right here is going to give me my Coriolis acceleration. I'll go ahead and calculate that in a minute. And the very last term here is we've got this 3 meters per second squared. That's parallel to this velocity vector, so I'm going to put plus 3I. Okay, so I think I got everything. So again, I want to go through these. This is a 0 because O is not accelerating. This guy right here is the centripetal acceleration due to this angular velocity, and I would like to point out at this point that has to do with this blue velocity vector right here changing in direction. So this velocity vector's change in direction is already taken into account by the time we do this term. Let's see, this guy right here, R alpha, this is for the tangential acceleration. That's this vector caused by this angular acceleration in the direction shown. This 2 angular velocity crossed with my velocity vector is for the Coriolis acceleration. That's for the fact that this velocity vector is changing in direction due to this angular velocity vector. And then lastly but not least here, this 3 meters per second squared is the acceleration of C with respect to O in the XY coordinate system. The XY that I've shown, the green one. So I think I got everything taken into account. I'll go ahead and put the units on this kind of outside now. Meter per second squared. We'll just do that. All right, equals. So I'm going to go ahead and clean this up. I've already went through and calculated these values here. I'm just going to copy the values that I have here. So we should end up with, if you give me just a moment, I want to make sure I put these in the right place. Let's see, I ended up with 0.4 in the minus j plus 1.8 in the minus I plus 12 in the minus j plus 3I. Again, meter per second squared. All right, so let me talk about which ones are coming from where. All right, this 0.4 here in the plus j, that was coming from this term. Whoops. Right here. I think I'm going to go back, pause this, and just double check every calculation here if you don't mind. Okay, I'm back here. I had worked this problem out ahead of time, and one of the little things I did here is I actually did these in a different order in my notes than I did when I wrote them in the video. So let me go through and kind of talk about where they're coming from term by term. So this 0.4 meter per second squared was in the minus j direction. Let me make that a little easier to read. I think I had plus j before. I double checked that was from minus j. That is coming from this term right here. This 1.8 meter per second squared is coming from this product. This 12 in the minus j meter per second squared is coming from the cross product part. So that's coming from this vector right there. That's my Coriolis acceleration. When I did the calculation, 2 times 3 times 2, there's your 12. The direction is coming from minus k cross I. And then plus 3 meter per second squared. And if we go ahead and add these up here, like terms, so we want to take this and add it to this. When we take 3i minus 1.8i, we get 1.2i, and then 12 in the minus j, 0.4 in the minus j. Let's do this, plus 12.4 minus j direction, Go ahead and put the units outside here, units of meter per second per second. So there's the acceleration vector of c with respect to O. Again, this is given in terms of this green coordinate system right here, which is rotating on the body, and it's perfectly fine. We could quite easily translate this to this coordinate system, but I'm not going to. Video's already at 15 minutes, so I think that's pretty well long enough. Again, important parts of this problem, when you write out some sort of relative acceleration equation, you've got to take all of these effects into account. You've got to look for centripetal accelerations due to rotation, tangential accelerations due to angular accelerations, Coriolis accelerations when you have a velocity vector that's rotating, like if you have a velocity vector in some set of coordinates like this, but the set of coordinates themselves are rotating with respect to some other coordinate system. And then the acceleration of the point with respect to the body and a fixed set of coordinates on the body. All of these effects have to be taken into account. Hopefully I've kind of demonstrated how to do that here. Have a great day.